Welcome to Introduction to Structures. Today we are going to be resolving a simple frame using robots, a software from Autodesk. So in this case, I have on the screen the scheme of the problem. So this is an isostatic frame. It's an inverted L that is fixed at the bottom of the column. So this is a column and this is a beam. And you have applied on this frame three forces, basically an horizontal force at the node B, a vertical load at the node F, and the UDLs from C to E. The dimensions are defined clearly here, and I have calculated by hand the reactions in the horizontal direction, in the vertical direction, and the reaction at the moment of this fixed support, just to check that the results I get from the software are correct. You can calculate as well by hand a few moments in different location of this structure, and the same thing with the axial forces and shear forces to check that the software is giving you the right results. This is especially important when you are learning the software in order to get confidence. Once you are confident using the software, you won't need to run hand calculations, but it's always a good advice to not to believe in the first instant the result you are getting from a software, but to try to make sense of the result running a few hand calculations even in your head directly to be sure that the results are correct. So let me go to now to robot. So I have opened robot in here, and as you see, the problem we are trying to solve in here is a frame in two dimensions. So it's really important to select the right problem when you start an analysis in robots. So we are going to, you click in new, you have several options to make analysis in here. And in this case, it's important to select the two-dimensional frames, because if not, you will have some problems introducing the loads and defining the restrictions or adding the support to your structure. A common mistake is to select trusses to make frames, and this is a problem because a truss by nature and by definition is a structure that receives only punctual loads at the nodes, so it's not possible to define UDLs, for example, as in our case, and it's not possible even to define a fixed support. So it's important to select the right problem to start. So we are going to select this frame in two dimensions, and as you can see, we are going to need to create several nodes to define the bars of this structure. And something to take into account is that you need as many nodes as punctual load you have, and you need a couple of nodes to define a UDL, because, for example, to define this UDL, you will need to be able to select a bar from C to E. So you need to create two nodes, C and E, to define this bar and to be able to assign the UDL to that bar. If you create a bar from C to F, you won't be able to define the loads properly as in this scheme. You need nodes in every point where you have punctual loads, and you need the node as well for the fixed support, as I mentioned before. So let's start creating the nodes then. The first node will be the node A that the software will call 1, and is going to be located at the original coordinates. So in this software, in order to start an analysis, you need to start opening this window in here, and selecting nodes is the first step for your for the definition of your problem. You will follow defining the members or bars, the cross sections, the support locations, and the type of supports and the loads, and after that you will be able to run the problem. So we are going to start clicking in nodes and identifying the original coordinate is 0, 0. See, if I click in there, I directly have created the first nodes at these coordinates. For the second node that you can see in the scheme is at 3 meters from A in the vertical direction. I just need to basically to locate the point, zooming in. So this is 3, this is 0. If I click in there, I have created the second node. The third node will be at 2.56 meters from B. So I will need to use the coordinates in here. So I will then introduce the second coordinate. The first coordinate 0 is the x coordinate. The z coordinate will be 5.56, and I will add the node, and I have created the third node that corresponds to the point C in our structure, in our scheme. So the next one, the next node I will create is going to be the node E, that is at 3 meters in the x direction. So I will say that the coordinate in the x direction will be 3 meters. I will add a comma to distinguish from the second coordinate. The second coordinate is 5.56, and I will add, and I have the next node created. Finally, the last node, as you can see in the scheme, is at 1.1 meters from E. So this means that the coordinate of the final node will be 4.1 in the x direction and 5.56 in the z direction. So adding this node, I have all the nodes I need to create this structure. So now it's time to create the creation of the bars, the software called members. So I will click in members, and I will start clicking in 1 and 2 to create the first member, from 2 to 3 for the second member, 3 to 4 for the third member, and 4 to 5 for the last member of this frame. So we have 4 bars created now, and we have all the nodes we need. Let's go to define the cross section for this structure. You can create and you can use the libraries of cross sections of the software, but let's do this exercise with a simple cross section. For example, is selected in this case this section of 100 times 100 millimeters and a square cross section, solid, but you can create any other shape, any other combination. So just to show you how to assign the geometry, for example, if you are going to change this cross section, instead of the one that is selected at the moment, we are going to use this 200 times 200 square again. So you just select the cross section you want, and you click in the bars where you want to assign this cross section, and that's all. So now we have this cross section called rect 2, that is 200 times 200 millimeters, and it's a square and solid. The next step in the definition of this problem will be the location of the supports. So you see that I have created in here several supports, but the one we're going to use is called fixed support, because the fixed support basically is a support, as you know, that restrict the displacements in the horizontal direction, in the vertical direction, and the rotations around an axis perpendicular to the screen. So I will just close this and assign the fixed support at the bottom of this frame. And the only need I need to define now is, in order to start the calculation, are the loads. So in order to assign the loads, what I'm going to do is I'm going to create a case load, a load case, sorry, because I want to see the results of the action of all the loads together. So don't avoid creating several load cases for every load, because if you do that, you will have result for every load case instead of having the result of all the loads acting together. Because I'm not interested in including in the self weight of the structure, I will create directly a leaf load case, selecting leaf and clicking in add. And even when the software include automatically the self weight of the structure, I will delete it after to run my calculations. Once I have created the load case, is the only one I will create for this problem, I will click in this button to start introducing the loads. Just to remember the load we have, these are the ones. So 30 kilonewtons in the horizontal direction at B, 20 kilonewton at F, and this UDL of 10 kilonewton per meter on part of the beam. Sorry for that. So I will move this to my other screen, and I will start adding loads in here. So I will select this button to add the horizontal a force of 30 kilonewtons at this node to in here, so I will show the nodes just for clarity. So the value of the force will be 30 kilonewtons in x direction, and z direction will be 0. So once I have defined the components of this force, I can click in add and click in the node, and I have added the first punctual loads. The second punctual load is at the end of the frame, and it's in the z direction, and the value is 20 kilonewtons, and in the component in the x direction is 0. So once I have the components, I click in add and I click in the nodes. As you see, the direction is not correct because in our scheme the direction of 20 kilonewtons is coming down. So I will correct it in this table I have in here directly, because in here you have the resume of all the forces you are applying to your extractor. So instead of having 20 kilonewtons, I will add a minus and I will click enter, and I will have corrected the direction of the force applied at the node 5. Finally, to add the UDL, I will click in member, I will choose to work with UDL, I will define the value of minus 10 kilonewton per meter that is defined already, I will add, I will click in the bar, and I have the loads as I want it. As I mentioned before, I'm not interested in this self-weight in this case, so I will cut this row of this table, and now I have all the loads I will consider in my calculations. So once I have defined my problem, I will click in this calculator to run the calculation. As you see, it's taken less than a second, and now I will be able to check the results. In terms of post-processing, I have to go to results and click in results again. So I can see all sorts of results in here, including stresses, but just to keep it simple, I will just focus on a few of them. So for example, if you want to see the reactions, let's start for the simplest things to do. I will select reactions. I will click in this 3 reactions that this fixed support has. So a reaction in the horizontal direction, in the vertical direction, and a reaction as a moment, and I will click in descriptions to see the values. So once I click in apply, I will see the values and the directions of the different reactions, and this is a value I have calculated by hand as well, so the results are apparently correct. So I'm happy with the reactions. I can go and see other results now. So for example, you can add directly in the post-process and add to the reactions you are showing at the moment the moments, and apply. And in order to see them with more clarity, you can go to parameters and select, for example, labels, differentiate between positive and negative, and fill the diagrams. So it's more clear, it's clearer now, but you can even improve clarity of this diagram, increasing the scale of these diagrams, clicking this plus or minus. You have control of the size, or not the size, but the scale you are using for showing the diagram. So in this case, it's clearly the distribution of moment in this frame makes sense. I can run some very simple calculation of moment at the point E, for example, is 20 times 1.1, so correspond to the one calculated by the software. I can do the same at the point C, or at any point actually, because this extractor is extremely simple, and I see that the results in terms of moment make sense. In terms of other internal forces, for example, let's say, what is this Fx force? I will apply. So checking the result, you see that this represents the compression on the column, and there is no compression in this beam because there is no any force producing compression or tension on the beam. So the beam is free of actual internal forces, but the column is subjected to a compression of 50 kilonewtons. If I delete Fx and I show Fz, what I see here is that the shear stress on the column is from 1 to 2 equal to 30. There is no shear stress in the column from 2 to 3, and the distribution of the shear forces, sorry, they are not shear stresses, they are shear forces, are, as you see in this diagram, starting with 50, reducing linearly to 20, and closing the diagram at the end with 20 kilonewton, which is basically the force you have in here. So if you are accustomed to sketch bending moment diagrams, shear force diagrams, and axial force diagrams, you will recognize that this is correct, and this is the way you can read the results in terms of internal forces and in terms of reactions. You can do the same with the stresses and other values in the post-processing for more complex structures, or for this structure you can do the stresses as well. But for now, I think this is enough for the purpose of this video. So thank you very much for watching.